Do you guys know how the Johnson counters work? So here is the thing that how we can convert the ring counter into a Johnson counter. So in ring counter, what we have seen is the output, the last the bit at the leftmost flip flop will be connected to the rightmost bit will be connected to the leftmost flip flop. So that is what the ring counter will work. But when we toggle the Q0 and we fed that back to the our Q3 or leftmost flip flop, then this is called as a Johnson counter. So here you may see because of this inversion what will happen, but you guys will see the result that is very amazing. So first clock pulse what will happen? So this will be flip and 0 inversion is 1, so 1 0 0 0 will happen. So 2 3 4 5 6 7 clock pulse. Okay, so then what will happen? This will again flip 1 1 0 0 1 1 1 0 1 1 1 1, right? So then 0 1 1 1, so 0 0 1 1 0 0 0 1. Then again if you do, then the first state will resemble. So here if you see, there is clearly an 8 stage of things is happening. So that is nothing but 2n. So used state is 2n. So used state which is equal to 2 into n. Okay, so that much state of used thing. So output frequency, how that will be divided? So that will be equal to f clock divided by 2n. Okay, so here you can see some kind of improvement that is happened. So duty cycle will be ultimately equal to 50%. So that much of improvement that is happening because of just we are adding an inverter to the thing. So in ring counter what happened? So we'll be just having a same thing. So like how the for n number of states only will be used, but here some extra n, that means 2 power n, 2n number of states can be used. So here is one simple question. So the 3-stage Johnson counter. So question. So here the 3-stage Johnson counter. So you guys can try this one. This will be very easy. So 3-stage Johnson counter as shown below is clocked at FC. So FC is the clock frequency that we are giving from state Q0, Q1, Q2. So they are given some the order of the sequences will be. So let me draw the circuit. Okay, so this everything is a JK flip flop. So just J0, K0, Q0, Q0 bar. So J1, K1, Q1, Q1 bar. So J2, K2, Q2, Q2 bar. Okay, so this is how. So every clock is synchronized. So clock is synchronized. So this is clock. So which is positive edge triggered clock which is applied to everything. Okay, so then the last state from the Q0, everything is sequentially connected. Okay, so the last state is fed to K0. Okay, so this Q2 bar which is connected to J0. Okay, so now we are going to analyze the thing. The condition is that they are given the initial condition as it is. So 0, 1, 0. So they're asking us what will be the output frequency. So 3-state Johnson ring counter as shown below is clocked at the constant frequency f starting from thing. So they're asking us what will be means they are asking about the clock frequency, that output frequency at the Q2. So you guys may pause the video and try to answer it. So we have previously seen that Johnson counter will have 2n state, so 2n used state. So we can clearly state that f naught, which is equal to f clock divided by 2n. So here n is 3-bit storing, so f naught can be equal to f clock divided by 6. So if you guys able to get this answer, then this is wrong. So because we should not solve this one like this way. So this is possible only when our initial condition is 0, 0, 0. So when our initial condition, which is equal to 0, 0, 0. But here the initial condition is 1, 0, 1. So then we may not know how the patterns will be there. So as we know, this is a pseudo random counter. So this will not follow the uniform steps everywhere. So now we have to analyze it carefully. So let us analyze it carefully. So if we take the thing, so here I am writing clock. So Q0, Q1, Q2. So initial condition at the 0th clock, the initial condition will be 1, 0, 1. So then what we are doing, we are fetching. This is we know this is Johnson counter. So the reverse will be given to here. So actually the circuit here they are giving, right? So this is Johnson counter. So how the thing is that when we connect the positive of the last flip flop to K and this to there, so this will just simply act as a toggle. So if we provide J and K, which is equal to 1, so this is also connected directly, it will be connected. So this is also Johnson counter. So you guys can note it. So even if you guys can use this, solve this one using the characteristic equation. So if both the input are fed like this and the reverse is connected, then this will also act as a toggling. So output it will be toggle and that will be fetched to the thing. So that is what we are considering this as a Johnson flip-flop. So sorry, Johnson counter. Okay. So let's directly solve our thing with the help of using that one. So we know the Johnson counter, the last bit will be flipped. So during the first clock, this will be flipped to 0, 1, 0. During second clock, what will happen? This will be 1, 0, 1. Third, 0, 1, 0. So this is already repeated, right? So fourth is also 1, 0, 1. So here we can clearly state only 2 states is coming. Okay. So based upon the structures, the state will vary. So you guys cannot blindly believe that every time the Johnson counter will have 2n state. Because based upon the initial condition, it will vary. So the f naught will be equal to fc divided by 2. So this is what the correct answer, guys. So please make note of it. So the output will be f naught or fc divided by 2. Okay. So this is what the output state frequency it will look like. So I think you guys able to understand the things, right? So this is how we need to solve the question in the counter. Any counter, just don't leave blind go with the formula, because there will be many tricks to make us wrong. So follow these kind of things to get a correct answer there. So counters are used to count the clock pulses. So simple thing. So counters are also used to clock the count pulse. Count the number of pulses, number of clock pulses. Okay. So it can be used in many applications. Like it can also be used in frequency measurements. Frequency measurements. Time measurement, because frequency time are inversely related, right? So we can also find out the time measurement. And also pulse with modulation, pulse with measurement. So that thing can also be done here. So there is a pulse with measurement. So that can also be done here. Okay, so these are some kind of application we can use in clock. So mod n counter. So if we state them as a mod n counter, so it will count n different states. So previously we saw, right, so ring counter, Johnson counter, that are random pseudo random sequence counter. But here when we represent that as a mod counter, that will be uniformly distributed, means that will count from 0 to n minus 1. So this is some assured state of representation. So every time it will have n number of states, that will from 0 to n minus 1. So that is what the thing. So how the counter basics will work is that the modulus of counter. So now we referred, right? So modulus of counter is the thing, that is some analysis that we have to do to design the counters. So there is two types of problem they can ask. They usually ask analysis problem only. Sometimes they may ask even the creation problem, like we have to design the circuit, like that also they can ask it. So number of flip-flops needed. So number of flip-flops in mod n. If there is a mod n counter means number of flip-flops needed is that. How we can analyze this thing is that log 2n. So number of state to that of log power n. Or we can even use this one. So log 2 max count plus 1. Both are same, right? So n we are also representing like this way. So for an example, you are having a mod 16 counter. Mod 16 counter. Then how we can find number of flip-flop needed is that. So here it will work from 0 to 15 states. So we can directly write this as a log 216. So which will be equal to 4. So the output clock frequency will be divided by fc divided by 4. So this is how it will work. So this way we can directly find it. So for an example, if random counting are given, so 0 to 3 to 5, 7 and again 0. So this is also one kind of counter. So this is not a mod counter, this is a random counter. So what we have to do is that this is also mod counter only. This is similar to mod 4 counter because 4 states are counted. But here if you see, there is not a pattern, that is not uniform or sequential pattern. So something will vary. So in this case, how we can find the number of things represented is that here you can try like this way. So if we try, there is 4 state. So this is 4, then output will be 2. This is wrong because the 7 is there, right? So 7 can be represented only in 3-bit number. So if we go for thing, so the greater than 2 means then we need a 3. So it will be proxy equal to 3. So we need 3 flip-flops here. So this is how we have to find out how many flip-flops is needed to represent that particular circuit. Okay, so like this way only we have to we need to analyze the sequences in order to get the thing. So if two counters are cascaded, so cascaded counters, cascade connection of counters. So if mod m, it has m states which is cascaded to mod m, mod n. So mod n state. So both are cascaded means then output will be mod m into n. So mn. So this is how when we cascaded, the number of states that we can do is like this. For an example, if mod 5 counter is cascaded with the mod 2 counter, then it will similarly work like mod 10 counter. So 10 number of different state it will be counting. So this is how we can the cascading structure will work. So we have already seen a pulse measurement can be done in counter. So pulse width measurement. So this is one kind of application, right? So let us see how this is done. So pulse measurement can be done using counter. So how the pulse width, usually pulse width how it will be. So it will start from here and it will be up and it will go for some period of time. This width, how long it is one, that thing is a pulse width. So that is what we have to count. In the RAS condition we already discussed thing, right? So this pulse width. So here is the counter. So whenever the pulse width is starting, the counter will go count. So it will count. Then it will come down. Again the pulse width is 1. So the clock is triggered, the counter output will be changed. So here again the counter is 1. So the clock input will be changed. So similarly, how many times the clock pulse is changing? So based upon this trigger, some delay can also happen here. So this is. So how many times the thing can vary, which is based upon the pulse width. So based upon the number of things, number of times the counter output changes or any kind of things happening, we can able to find out the pulse width. So how this is done is that, so here if you see the entire pulse width duration, so this is the entire pulse width duration, that is a pulse width duration. So here if you see 3 clock pulse, so 3 clock pulses has been taken. So 3 times there is a change in the TC, means the clock pulse taken 3 pulse. So we can directly say that is 3 into TC. So 3 into, so if it is 5 milliseconds means we can state that as a 15 milliseconds is the total duration of the pulse. So max error, because there is some error, right? So this transition is not included. So this transition is not included. So that is some max error is also possible. So the max error is will be TC. Okay, because up to 1 TC it will may not do. So TC is the duration of the next thing. So up to this one. So this is the TC. So 1 TC of error is possible because for the next clock pulse is need to trigger, it will take some TC time. So if it is if the change in output is happened here, and 1 TC is not, if the 1 TC is the pulse with extra duration which is remaining, which is less than the 1 TC, then the another counter will not happen. So in this case, the error is also possible here. So the max error possible is 1 TC. So I hope you guys able to understand, right? So for an example, if the 3 transition has happened here, instead of A or C, so this one is also not included. So here if you see, this one is also not included. So here we can state that even an extra error. So here you see 1 TC. So this is another TC. So this is another TC. So here you see, here up to here we have included in the clock pulse. So this error, what this error can be, this is error. So max of this error will be TC. So max will be TC. So I hope you guys are able to understand, right? So sometimes it may be is the accurate 100% accurate is possible. Sometimes if we randomly choose a TC that is exactly aligned with the multiples of TC, multiples of pulse width. So this is what the pulse width, right? So if the TC which is a multiple of, if a TC which is directly proportional to n of TW, then no error. But that is always, this is not possible. So no error, but that is not possible always. But if there is some miscellaneous or some kind of extra things is that come, so in that thing the error will happen. So that error is max is TC. Okay, so I hope you guys able to understand that. So how we can measure the frequency is that if we enable the counter for 1 second, then the output counter indicates the number of frequency. So we already know, right? So based upon number of things, so we can, so if is fc divided by n. So based upon this, we can able to find out the output frequency, and from this time also we can calculate. So this is how all the application that are resembling with the counters. So I hope you guys had a good understanding on the ring counter and Johnson counter. So from next class, we will be seeing the sequential counter. So how we can design the circuit, how we can analyze the circuit, how counter circuit. So let's discuss all the things detailedly from next class. So stay tuned, guys. So like, share, and subscribe our channel.